Okay, so is my screen visible to everyone? All right. Okay. Hi, everyone. So I hope you guys are doing good. So today we are going to be solving two problems based on DP plus combinatorics. One of them is going to be of an intermediate level, and the second one is going to be of somewhat hard level, right? So yeah, that's the plan today. And before starting, let me just go over the prerequisites for understanding the problems. So the prerequisites are that, first of all, obviously you should be familiar with basic dynamic programming. And secondly, you should be familiar with modular arithmetic. So you should be familiar with simple operations like addition, subtraction, and multiplication under the modulo sign, and obviously division. That is the most important of all. And thirdly, you should be familiar with basic combinatorics. That is, you should be aware how we have basically find the combinations of a number with respect to another number, basically how we find NCR values, right? So that is what you need to be familiar with, and what actually NCR values represent. Okay, so yeah, these are the basic prerequisites for the session, and I'll be walking through the problems, and then I'll give you some time to think about them, and then I'll go over the solution to the problems. And in between, if you guys have any doubts, you are free to unmute and ask any kind of doubts that you might have, right? So yeah, that's the plan for today. And with that, let's start with the first problem. I have already shared the links to both the problems in the Discord server, but for those of you who missed it, I will share them again in the chat box. So this is the first problem that we are going to be solving today, and I have shared the link in the chat box. It's called yet another problem on a subsequence. It is problem D from educational round 46 code forces, right? So yeah, let's just go over the problem statement, and then I'll give you guys 5 to 7 minutes to think about the problem, and we can discuss various approaches which come into your mind. Okay, so yeah, this is the problem statement. So a sequence of integers a1, a2 up till ak is called a good array if a1 is equal to k minus 1 and a1 is greater than 0. So basically, a sequence is a good array if its first element is equal to the length of the sequence minus 1, and the remaining elements can be any and everything at all, right? So there is no constraint on the remaining elements, but for an array to be a good array, its first element should be equal to the length of the array minus 1, and also its first element should be strictly positive. So yeah, that's the definition of a good array. And a sequence of integers is called good if it can be divided into a positive number of good arrays, right? So basically, we need to divide an array into some subarrays such that every subarray is a good array, right? So if we can do that, then that particular sequence is called a good sequence, right? So each good array should be a subsegment of sequences, and each element of the sequence should belong to exactly one array, right? So that just means that we need to divide the array into subsegments such that each subsegment is a good array and every element belongs to exactly one subsegment. Okay, so I hope the definition of a good sequence and of a good array are both clear. Okay, so now comes the main problem. The main problem is that we are given a sequence of numbers and we need to count the number of its subsequences, which are good sequences. Okay, I know the problem statement is a bit involved and there are a lot of terms used here like good array, good sequence, and subsequence, things like that. But if you are strong with basic definitions and if your basics are strong, I don't think it's very difficult to understand the problem statement at least. So we have an array, and what we need to tell is we need to tell the number of subsequences of this array that are good sequences. And a good sequence is a sequence which can be divided into contiguous subarrays such that each subarray is a good array, right? So yeah, we need to find total number of good subsequences of our given array modulo this prime number. And that's the entire statement. Notice that the constraints are a bit weird here, that n is up to 10 to the 3 and not 10 to the 5. So that is surely going to be helpful for us. And yeah, so we have an array and all the elements are up to 10 to the 9, from minus 10 to 9 to plus 10 to 9. So that's the problem statement. If you have any difficulties in understanding what the problem is saying, then you are free to ask. Otherwise, I'll give you guys 5 to 7 minutes to think about any possible approaches which comes to your mind. And if at all you think of something, then you are free to unmute yourself and we can discuss it here before I talk about the solution. Yeah, so a subsequence is basically a sequence of integers which you get by removing certain integers and preserving the position of all the other integers in a sequence, right? So it is not necessarily contiguous. A subsequence is a standard term in competitive programming. Basically, you have an array and you take out some elements, some 0 or more elements at random positions of the array. And then whatever is left, you just concatenate everything. And what you get is a subsequence. Okay, so if there are any other doubts, you can still ask. And if you have any approaches, then we can discuss them.
Can you give the link?
Yeah, I have shared the link in the chat box.
Okay.
So since this is a DP plus combinatorics based session, then it's probably helpful if you think in the direction of dynamic programming. So we can at least discuss what states our DP should represent here. So any guesses, any ideas, anyone? Okay. DPI is the count of good subsequences in the range I to N maybe. Awesome, awesome. So that is correct. So this is what we will be doing. We will be keeping a DP array where DP of I will represent the count of good subsequences in the suffix starting from I. Great.
Sorry, actually, I did not understand the problem statement itself.
Yeah. So
Can you go over the first test case, please?
okay, okay. So let's see. So first of all, they have defined the definition of a good array. A good array is just a sequence whose first element is equal to the length of the sequence, the length of the array minus 1, right? So there is this array A1, A2 up till AK. It's called a good array if A1 is equal to K minus 1 and the rest of the elements can be anything. Also, A1 should be positive. Okay, so I hope the definition of a good array is clear, right? And secondly, they have defined the, yeah. So now they have defined the definition of a good sequence. So a good sequence is nothing but a sequence which is a concatenation of several good arrays, right? So it is a sequence which can be divided into contiguous subarrays such that every subarray is a good array. Okay. So is the definition of a good sequence clear?
Okay.
Yeah. So now what they are asking is they have provided us an array and they are asking the number of subsequences of this array, which are good sequences. Okay. So I hope the definition, the problem statement is clear.
Yeah.
Yeah. So these recordings will be uploaded on YouTube, Divyanshu. So you can access them later on my channel. Okay. So
these are not contiguous, right?
Yeah. Subsequences need not be contiguous, but a good sequence has to. Sorry.
Okay, so this is just a partition problem. I mean, we are just partitioning. It's not contiguous.
So basically, if you have a subsequence, then you need to divide it into partitions, but a subsequence need not be contiguous.
I see. Okay.
So I'll give 2 more minutes to you guys to think about it, and then I'll start going over the solution. Meanwhile, if someone has any approaches, so Prabhav is on the right track. He says that we'll keep a DP array. So if anybody can talk about the transitions here, then that'll be great. So Sanchit says that with the above DP, we can go backwards and count for all subsequences by taking current into account. So for transition, we can start by choosing some elements j such that j minus I plus 1 is greater than or equals to ai. Great, great. So all of you are going in the right track. So yeah, this is correct. This is what we are going to do. We are going to iterate for a j such that j minus I plus 1 is at least ai. All right, I'll just give 1 more minute for you guys to think about it. And okay, so dpi is summation of dpi minus ai minus 1 up till n. Um, Actually, that won't be correct. That would not be correct. Because according to you, the definition of DPI is that the number of good subsequences which start at the index I. So there is no relation between previous values between DP of I and DP of J such that J is less than I. There will be relation between DP of I and DP of J if DP of J is if J is greater than I, right, Prabhav? So like there is no relation between left values from the right values. So Ansh says, let L is equals to J minus I plus 1. Then I'm not able to understand what you've written here, Ansh. Okay, so he says L choose K minus 1 plus dp of J plus 1. So Ansh is really close, although the expression is not correct, but again, he's on the right track. Okay, so I think everyone is thinking, and that's good. So let's just go over the solution now. All right. So let's start by writing down some definitions. So good array. An array such that first element is equal to length minus 1 and first element is greater than 0. So that is a good array. And the second thing is a good sequence. A good sequence is nothing but a concatenation of good arrays. Any sequence which can be written as a concatenation of good arrays. So that is nothing but a good sequence. So the problem is count the number of subsequences of the array which can be written as concatenation of good arrays. Okay, So yeah, this is the problem statement. And we are going to be using dynamic programming to solve this. And we'll make use of this very interesting constraint that n is only up to 1000. And when n is up to 1000, then it is almost always the case that there is an O of n square, and in some rare cases, an O of n square log n solution. So yeah, we'll think about an O of n square solution. But the problem is that since we are trying to use dynamic programming, should we keep our DP array as a 1D DP array or a 2D DP array? Because this small constraint is sometimes an indication that we need to have a 2D DP array, right? So in cases like this, what I generally do is I start with just keeping one dimension, and then I try to do everything, all the transitions using this one dimension. And if some information is missing, then I immediately know that that particular information is going to be in my second dimension. And if at all I don't find any missing information, then one dimension is good enough. So what we'll do is we'll start by just keeping a single dimension. Okay. So let's keep a simple 1D DP array where DP of I represents the number of subsequences, number of good subsequences starting from the ith position. So this is the definition of DP which I am taking. And as we'll see later, it will be sufficient. This particular one-dimensional DP array is going to be sufficient to solve this problem. But the definition of DP is that DP of I stores the count of number of good subsequences of the array which start at the ith position. That is, the first element of the subsequences is A of I, right? So yeah, so now let's talk about base cases and transitions. So I'll tell you guys the base case and then I'll ask for transitions. So the base case is that if I have an empty array, that is DP of n plus 1 is going to be 1. Why? Because this is just an empty sequence, and for an empty sequence, the answer is definitely going to be 1. Okay. So yeah, this is the base case that DP of n plus 1 is equal to 1. But now, what about the transitions? So yeah, can anybody tell me what transitions we are going to have here? Obviously, since n is up to 10 to the 3, the transitions are not going to be really simple. We need to do some kind of iterations to figure out the exact transitions. So how do we exactly do them? Some people have already mentioned some of the expressions, uh, which are really close to what the correct expression would be. All right. So what we are going to do is, since the subsequence should be a concatenation of several good arrays, what we'll do is, we know that our subsequence is starting at A of I, right? So we will iterate on the starting of the second good subarray, the second good array of the subsequence. Obviously, the starting of the first good array is I itself. But what we can do is we can iterate on the starting of the second good array that will be a part of the subsequence. Okay. So we will iterate for j from I plus 1 to n such that A of j is the first element in the second good array of the subsequence. Right? So if this is not clear, you can ask again. The thing is that we know that our subsequence is any subsequence, any good subsequence which starts at the ith position is a concatenation of several good arrays, right? So we know that the first good array starts at the ith position, but we don't know where the second good subarray starts, right? So we will iterate on the position j, and j is the position where the second good array is starting. Right? A of j is the element which will be the first element of the second good array out of an arbitrary number of good arrays which are possible uh, for any subsequence which starts at the ith position. Right? So I hope what I'm doing here is clear enough. Right. So yeah, now we are iterating on j and we are saying that this is our subsequence, let's say. There will be multiple values in this subsequence, and we know that a subsequence is divided into several good arrays, right? So let's say that this is the first good array, this is the second good array, and so on and so forth. We know that this is the position I, and this is the position J where the second good subarray is starting, right? So now, can anybody tell me what kind of transitions are we going to have here? Also, forget about the transitions. Can anybody tell me how many elements should be there in this particular range in the first subarray? Remember, the definition of a good array is that the length, the first element should be equal to length minus 1, right? So how many elements should be there in the first array if it is starting from the ith element? This is a really easy problem. So anyone can write it in the chat box. Okay, Ansh says at least a of I. Why should it be at least a of I? Shouldn't it be exactly a of I? Because I'm only talking about the first good array. Yeah, so Chand is correct. It should be a of I plus 1. Why? Because I'm only talking about the first good array, and the definition of a good array is that its length should be equal to the first element plus 1. Okay, so what I'm asking Natwar is that the subsequence which I'm interested in would be divided into several good arrays, right? So how many elements should be there in the first good array if the first good array starts at the ith position? And I am getting some right answers, and the answer is a of I plus 1. So there will be a of I plus 1 elements. So there will be a of I plus 1 elements in the first good array. Okay. So that means that in this range from I plus 1 to j minus 1, there should be a of I plus 1 elements. So in the range from I plus 1 to j minus 1, there can be any arbitrary number, any arbitrary a of I plus 1 elements that can be a part of my subsequence, right? So yeah, so like there is this range from I plus 1 to j minus 1, and I can choose any ai plus 1, any ai elements. Sorry, this plus 1 should not be there because ai already contributes 1. So the remaining elements is just ai. So yeah, in this range from I plus 1 to j minus 1, I have to choose ai arbitrary elements, and I can choose any ai elements because the only constraint that I have is that the length should be equal to the first element plus 1. So I can choose any arbitrary ai element in this elements in this range from I plus 1 to j minus 1. And once I do that, then the problem reduces to finding the number of good subsequences which start at the position j. So let me write it down more formally. So dp of I is choosing any ai elements. So Prabhav says we'll choose ai elements from the range I plus 1 to j minus 1 multiplied by dp of j plus dp of j plus 1 up till dp of n. So we'll maintain a suffix dp sum. Prabhav, I think you are almost correct, but the thing is that we don't need to multiply it with all the dp values in the suffix. We only need to multiply it with dp of j, and we'll see why. So yeah, let me get back here. So dp of I is choosing any ai elements from the range I plus 1 to j minus 1, and then counting the number of subsequences which are good and start at position j. So Prabhav, what you are missing here is that I am already iterating on j, right? The constraint is that n is up to 10 to the 3. So I am already iterating on j. So for a particular value of j, I will just choose AI elements in the range from I plus 1 to j minus 1 and multiply it with the count of good subsequences which start at position j. And count of good subsequences which start at position j is nothing but dp of j, right? So yeah, now I have my transitions with me. So can anybody tell me what is the number of ways of choosing any AI elements in the range from I plus 1 to j minus 1? So if you have basic knowledge of combinatorics, this problem should not be very difficult. We have to choose some AI elements in the range from I plus 1 to j minus 1. How many ways are there to do this? It's just a simple expression here. This is a range which contains j minus I minus 1 elements, and we need to choose any arbitrary AI elements, right? So Kasparov is right. We just have to choose AI elements among j minus I minus 1 random elements. So the number of ways to do that is nothing but j minus I minus 1 CAI, right? And once we do that, we just need to multiply it with the number of good subsequences which start at position j. So dp of I is nothing but this expression multiplied by dp of j. Okay. So yeah, this basically sums it up. So now we have our final transition. So dp of, so we remember that we were iterating on j. Okay. So for j going from I plus 1 to n plus 1, sum of c of j minus I minus 1 and ai multiplied by dp of j. So this is the transition. And since we are having a nested loop here, the time complexity of the entire problem becomes O of n square, which is good enough to tackle these small constraints of n up to 10 to the 3, right? Yeah, so we are doing n plus 1 because of our base case. Our base case here is that dp of n plus 1 is equal to 1. So basically, you can just get rid of this base case and you can write an extra condition here. So notice that I am always iterating on j, where j is the starting point of the second good array. But what if there is only one good array, right? That is an extra case. And to get rid of that extra case, what I do is I just simply assign dp of n plus 1 is equal to 1. And I iterate for j up till n plus 1. And that takes care of the case when there is exactly one good array. And yeah, so there is no need to iterate on the second good array. Great. Okay, so yeah, this basically completes the solution. So before I go ahead and code this up, if anybody has any kind of doubts in understanding what's going on here, you are free to ask by even unmuting yourself.
I have a question.
Yeah.
So, like, how are we saying ki these are the disjoint counting? Are we not like how are we ensuring there is no double counting? I get you that you have chosen J as arbitrary, and
Mhm.
like how does it
Okay,
ensure
okay.
this
Yeah.
particular?
So let's look at the definition of dp of I again. So dp of I counts the number of good subsequences which start at the position I. So there is this constraint that the subsequences should start at position I, right? And when I iterate from j, I am basically making sure that the good subsequences which are there, their second good subarray starts at position j, right? So if I'm making sure that everything starts at different positions, then I'm making sure that there is no double counting, right? So like the number of subsequences which I get from j and j plus 1 will all be different, because any subsequence which I get from a value j should have their second good subarray starting at position j, and any good subsequence which I will get from j plus 1 should have their second good subarray starting from j plus 1, right? So this makes sure that everything is disjoint and there is no double counting. I hope I was able to make it clear enough.
Yeah, it's clear. Thanks.
Okay. Any other doubts before I go ahead and code this up? The code is going to be really simple.
Am I audible?
Yeah, yeah.
Actually, I wanted to know that, like, I had the same doubt. So let's suppose you can you write down this example? Just wanted to make it a bit clear.
Okay.
Let's say you have three,
Mhm.
comma. Let's say you have let's say 3, 2, 1.
Okay.
Yeah, 3, 2, 1, and then
Mhm.
you have like let's say 1,000, 2,000, 3,000 in this way. 1000, 2000, 3000, and so on, like all very large values.
Okay.
So let's suppose your j is at 2000 and
Okay.
I is at 3, right? I mean, in this case, there should only be one possible answer. That is, let's suppose 3 to 1 or 3 and anything, right?
Yeah.
Uh,
Yeah.
yeah. So let's suppose your j is at 2000. So now, you have a range of from 2 to 2000. You have this range, and then you do a combinatorics,
Yeah. Yeah.
and then so over here you can get that uh, 2. Oh, actually,
We'll get
okay, okay.
three C2.
You don't. Okay, I mean, oh, I was confused. I mean, we can get 3, 2, 1, and 2000. We can get 3, 2, 1, and 1000,
Yeah.
right?
Yeah. Yeah. Yeah.
I
Yeah.
mean, anyway. So I thought that when, let's suppose j is at 3000,
Mm-hmm.
so we can again get 3, 2, 1, and 2000, and so on. But okay, okay, this makes sense. I mean, you're not doing dp of 5 plus equals. Oh, I'm
Yeah.
sorry.
So
Uh,
that will not happen. Why? Because
Okay.
dp of 3000, like 1, 2, 3, dp of 6 is going to be 0, right? Notice that
Uh,
dp of 6 is going to be 0. Why? Because
because
3000, let's say 3000 is the last element. So
okay,
dp of 6 is going to be 0. So what you are trying to say is that when j is at 2000, then I am choosing arbitrary 2 elements from these 3. And when j is at
yes,
3000, I'm choosing arbitrary 2 elements from these 4. And what you're
yes,
saying is that both of them can have overlapping values. But the thing is that
correct.
both of them won't contribute to my answer because dp of 6 is just going to be 0. And this is in multiplication here. So that will contribute 0. I hope I was able to make it clear to you.
But above you said that if there's no value, then dp of that thing is equal to 1, or
No,
I'm
that is
sorry if.
only for n plus 1.
Okay, okay, okay. Makes sense. Okay, okay. Sorry.
Yeah,
It's clear. Thank you.
great, great. All right, so if there are no more doubts, I think I should go ahead and code this up. All right. The code is going to be really simple and easy here. First of all, if you guys don't know how we actually calculate binomial coefficients, then I highly recommend you to learn them. You can learn it from anywhere, either from GFG or CP algorithms or anywhere. So that's totally up to you. I have this pre-written template code here, which calculates binomial coefficients. So I'm going to be using that. So do you guys want me to explain how exactly this works, this NCR thing works?
No, it's clear.
Okay, okay, great. So yeah, so this is the NCR part done. Now let's get to the code. So we have just an array in the input. All right, so now we'll declare our DP array. It will be of size n plus 2 and initialized with all zeros. And let's just get done with the base case that DP of n plus 1 is equal to 1. And try to understand why DP of n plus 1 is equal to 1 case is there. Well, it is just there so that we don't have to write this extra if condition where we will take into account the situation that the particular subsequence has exactly one good array, because when we iterate on j, we iterate on the starting point on the second good array. But what if there is only one good array? So dp of n plus 1 is equal to 1 takes care of that case. Okay, so now we'll iterate in reverse direction from n to 1. And obviously, if a of I is less than or equal to 0, it doesn't make sense to start any subsequence at the ith position, because according to the definition of a good array, a1 should be strictly positive. So if this is the case, we will simply continue. Otherwise, we will iterate. J goes from I plus 1 to n plus 1. And now we will calculate what we will add. So initially, this add variable is 0. And then what I'll do is this add variable is going to be dp of j multiplied by the combination of j minus I minus 1 with a of I. And we will take modulo. And then what we'll do is dp of I is dp of I plus add with the modulo. Okay. And also, can anybody tell me what will be my final answer here? I forgot to discuss about it. So what is going to be my final answer here? Once I have all these DP values, yeah. So my final answer is going to be the sum of all DP values. So I can just do it here only. Answer is equals to answer plus DP of I. Right? So yeah, this should probably work. Also, I don't think there are test cases here. Yeah, it makes sense. So let's just submit this. Okay, we got wrong answer on test 3. What's going on here? Okay, so I'm getting wrong answer in test 3. Why is that happening? Can anybody spot any errors there? J is equal to AI plus 1, right? Yeah, that is true, but that won't affect our answer because those values will just contribute 0. When j is less than AI plus 1, it will simply contribute 0. So that shouldn't affect anything. Hmm. Oh yeah, that's the problem. I forgot to change the modulo value, right? Thanks a lot. You saved me around 10 to 15 minutes of wrapping my head around this. So yeah, I have my standard modulo as 1e9 plus 7, but here this is the modulo value. Yeah. So now it should work. Okay, let's submit it again. Right, so this is done. So if anybody has any other doubts in this problem, you are still free to ask before we get to the next problem.
I have a doubt.
Yeah.
So how did you get the intuition of DP of I? So uh,
Yeah, so
basically the starting point. Yeah.
so obviously we have to work with starting points because the only constraint here is that the first element of a good array should be equal to length minus 1, right? So one thing was pretty clear, that we need to work with starting points. But if you are trying to ask me how I came to the intuition that we should have just a 1D DP array, then that is something which I already discussed. What I always do is I try to just minimize the number of states in the beginning, and I try to get done with it. And if there is some missing information, then I'm sure that that particular piece of information has to be included in the state of my DP. So that's generally how I go about solving such problems. But as far as the first element being concerned, then I think this particular condition, that the first element should be equal to length minus 1, should be a big enough hint that we should think about DP of I as I being the first element of a good subsequence. Okay. All right. Any other doubts? So if there are no doubts, then I'll move to the next problem, which is a bit harder than this one, and it's also really interesting. So yeah, if this problem is done, let's now move to the next problem, which we'll be doing. This is a very recent problem. It's actually from AdCoder Beginner Contest 243, problem F, and it was like the second hardest problem in the round. It was even harder than problem G, according to the number of solves. So yeah, it's going to be really interesting. I'll just share the link to the problem in the chat box. First of all, before even starting, I will just change my modulo. All right, so let's go over the problem now. So in this problem, basically, Takahashi is participating in a lottery, and each time he takes a draw, he gets one of the n prizes available. So there are n prizes, and every time I take out something from the draw, I will get one out of these n prizes. And the prize I is awarded with the probability Wi by summation of Wj for all j from 1 to n. So there is a weight associated with every prize, and the probability of getting the I prize is nothing but my weight divided by the total weight. Okay, so the result of the draws are independent of each other. So in every draw independently, the probability of getting the ith award is this expression. And so finally, what we need to tell is we need to tell the probability that we will get exactly m different prizes from k draws. So we need to find this probability modulo this number. And yeah, so this is the problem. This is just a very simple problem statement, as a general ad coder problem statement is very nice and neat problem statement, but the solution can get quite complicated sometimes. So also notice the constraints here that k is up till 50 and k is the number of draws, and mn are all up till 50. So the number of awards and the number of draws are all up till 50. So yeah, these are the constraints. The problem statement is simple. The solution is a bit involved. It requires probability, combinatorics, and dynamic programming. So yeah, if there are any doubts with the problem statement, you can ask, or else I'll give you guys 5 minutes to think about the solution. Also, I'm assuming that you guys are familiar with modular inverses and division under modulo, and how you can actually represent rational number modulo some prime number. So this is something that I'm assuming you guys already know. So yeah, if you guys have any approaches, you are free to share. Otherwise, I'll give you 5 minutes to calmly think about any approaches which come to your mind. Anybody has any ideas? You can either unmute yourself or you can write it in the chat box. So a hint is that the constraints are really small. So probably there have to be various dimensions in the DP array this time. Okay, so Kasparov says that he was thinking about meet in the middle kind of technique as it involves subset of size k. Okay, so one thing is that if these constraints were a bit small, like instead of 50, they were around of 25, then there was a very neat solution which involved DP plus bit masking. But unfortunately, that is not the case. And even I was thinking about something which which used meat in the middle, but I was not able to come up with an approach which would AC under these tight constraints. Yeah, obviously, if the constraints were a bit small, then there was a very neat TP with bit masking solution, but that is not a liberty that we have here. So I'll give 2 more minutes to think about it, and then we'll start with the solution.
I have one question.
Yeah, sure.
So, does he, like, after drawing one price, does he replace back into the bag?
Yeah, so there are an infinite number of prizes of each type. That is what this line that the result of each draw is independent of the other represents, that no matter which draw we are at, the probability of getting the ith prize remains constant. Even if we have already,
I see. Okay.
even if we already have 10 prizes of the ith type, we can still get the 11th prize of that type in the next draw. So it doesn't matter.
Yeah.
All right, so I'll give 2 more minutes. So there is no rush. Like, obviously, it's not very probable that you will be able to solve this problem in these 2 minutes. So I think it would be preferable if you can just think about what the states of RDP should be here. DP of draw and different prices. Awesome. So Prabhav is saying that we should have a 2D DP where one state should be the number of draws and the other state should be the number of distinct prices that we have. So this is really close to what actually our states are going to be. There is just one state missing here, which we'll define later. But awesome. This is really close to what the actual state should be. Great, great. So Kasparov says that we also need to know which prizes were taken. So this somewhat hints us towards the third state, which was missing here. But yeah, so we can like, if the constraints were small, then we can just very conveniently take a bit mask and figure out which are the prizes which are already taken. But we don't have that liberty here, right? So we have to think about something else. So we are almost very close to what the actual DP state will be. So let's just start with the solution now. Okay. So the problem is, yeah, so mask of prices which were repeated. So that would have been correct if the constraints were smaller. But since the constraints are up till 50, then obviously this won't work, right? So we won't be taking any kind of subsets, any kind of masks here. So all the states of our DP are going to be just numbers. So we need to find the probability of getting exactly m distinct prices after exactly k draws. So first thing which we'll do is that for each price, we will calculate its probability. So for each price, we define P of I as W of I upon sum of W of I. Right? So this can be pre-computed. So we will, for each price, we will compute the probability of getting this price in any turn. Great. So JM says that can third state be the previous selected price? So that is not what the third state would be, but it is something very close. So let's see. So what we are going to do is we are going to iterate on the prices, right? So we will start from the first price and we will go up till the last price, and we will maintain a DP array. So if we look at the problem, they are asking the number, they are asking the probability of getting exactly m different prices from exactly k draws. So it makes sense that we take both of these values into our state. So we will take both the number of draws and the number of distinct prices that we have got into our state. And since we are iterating on the prices from 1 to n, it is somewhat similar to when we iterate on an array. We iterate on an array from 1 to n, and we always keep at the index I as the state of our DP, right? So that is what we are going to do. So we will be having a 3D DP array where DP of I, j, k is going to represent the probability of getting exactly. So let's say that this is capital K, to not confuse. So DP of ijk is the probability of getting exactly k distinct prices after exactly j draws if we only take prices from the first I prices. So this is what our DP is going to represent. It is going to be the probability of getting exactly k distinct prices after exactly j draws, such that all the k distinct prices that I have gotten are in this prefix from 1 to I. Okay. So this is what DP of ijk is going to represent. So if somebody has any doubts in understanding what exactly this is representing, then you can ask. Otherwise, let's look at the base cases and the transitions. So first, the base case. Can anybody tell me what is going to be the base case here? So the base case is the case when I is equal to 0, since we are iterating from 0 to n. So the base case is when I have not looked at any of the prices and I is equal to 0. So obviously, when I haven't looked at any of the prices, the number of draws obviously is equal to 0 because there have been no prices. So the number of draws will be 0 and the number of distinct prices will also be 0. And the probability of this happening is 1, right? So dp of 0, 0, 0 is equal to 1. So this is the probability of getting 0 distinct prices if we only take into account the prices from 1 to 0, which is a null range, right? And the number of draws obviously will be 0. So dp000 is equal to 1. So this is our base case done. Now let's look at the transitions. So what we are going to do today is, generally we do a DP which is called pull DP. But today, to solve this problem, what we are going to do is we are going to do something known as push DP. So I'll write down both these terms and their definitions. So in pull DP, what we do is when we reach a state, we use the previously calculated DP values. We use the DP values of the previous states from which we can reach the current state to update the DP value of the current state, right? So this is generally what we do. And this is known as pull DP. When we reach a current state, we go over all the states from which we can reach the current states and use those DP values to update the DP value of the current state. But today what we are going to do here is we are going to do something known as push DP. So in push DP, what we do is when we reach the current state, we make sure that the DP value of the current state is already computed. And then what we do is we update the DP value of all the states which are reachable from the current state, right? So this is the definition of push DP, and this is what we are going to do here. So when we reach a current state, we will make sure that we already have the DP value of the current state calculated. And using this current DP value, we will update all the DP values of the states which are reachable from the current state. So is this clear? Is the definition of push DP and pull DP and their differences clear? So is it clear what we are exactly going to do here? If it's clear, you can just write it in the chat box. Yeah, so it is kind of like top down and bottom up, but there is no recursion involved here. Everything is going to be iterative. Actually, it's like it is not related to top down and bottom up at all. But the thing is that in iterative DP, there are two ways to do it. One way is pull DP, where when you are at the current state, you look at all the previous values of the states from which you can reach the current state. And using those values, you update the DP value of the current state. For example, what you do is, let's say you are calculating Fibonacci numbers. So what you do is dp of I is dp of I minus 1 plus dp of I minus 2. So this is called pull dp. You use the values of the previous states to calculate the values of the current state. But if we want to use push dp to calculate the value of Fibonacci numbers, then what we'll do is from I, the number I will contribute to the dp values of I plus 1 and I plus 2. So we will write two values, dp of I plus 1 plus equal to dp of I and dp of I plus 2 plus equals to dp of I. So we are making sure that we already know what dp of I is. And from the state I, we can go to I plus 1 and I plus 2. So we'll do dp of I plus 1 plus equal to dp of I. Similarly, dp of I plus 2 plus equal to dp of I. Great. So these are the basic differences. Okay. All right. So yeah, this is what we are going to do. So now let's look at the transitions. So what we'll do is, let's say we are at the current state I, j, k. So we have looked at the first I prices, and there have been j draws, and we have got k distinct prices. So now what we'll do is we'll look at the I plus 1th price. So now we will look at the I plus 1th price. Okay, so notice that both N, M, K are all up till 50, and we have 3 states in our DP. So the time complexity of our solution currently looks like 50 cube. But we are allowed a time complexity up till 50 raised to the power 4 because that will be well within our time limits. Yeah, Kasparov, you can unmute yourself and ask the question. Or maybe write
Yeah,
it in.
so
Yeah,
I was wondering. So I have two particular
yeah, yeah,
questions. First is like how does this prefix like picking up sets like subsets from the prefix ensure disjointness
yeah, yeah,
and because it's not very intuitive to me
yeah, yeah.
um, and secondly, yeah, the second question follows from this only, like how did you develop this intuition, or where like which particular questions like similar patterns we can think of this prefix picking.
Okay,
um,
okay, okay. So when I will explain you how we actually transition, then it will become very clear that why this actually works and why we don't really need a bit mask. So let's wait for the transitions, and I'm sure that you will understand why this prefix thing is working and why we don't really need a bit mask. And secondly, to be honest, when I tried this problem, I was not able to solve it. Even during the contest, I was not able to solve it. And many of the experienced people indeed were also not able to solve this problem. There were around only 200 to 250 accepted submissions, and that number is really, really low. So yeah, I admit that this problem is really hard, and I was not even able to understand the editorial. So I wrapped my head around it for a lot of time. And finally, when I was going through the Code Forces blog of this contest, then I read a comment where someone had explained the solution. And from there, I was able to figure out and connect the dots. So yeah, this idea is not very trivial, obviously. And to practice similar problems, I think there are a few problems on Code Forces whose difficulty level is obviously not this high. But there is this problem called armchairs, which I remember correctly, which used a very similar idea. So yeah, you can look at a few problems. So I remember this problem armchairs from Code Forces. You can search it and try to solve it. It is very easy, but it utilizes this idea of prefix, right? So yeah, there's that. So okay,
awesome.
so
So
with
yeah,
this, let's look at the transitions. So when we are at the state ijk, we will look at all the states which are reachable from the state ijk. So now we are going to look at the I plus 1th price. So what we'll do is, obviously right now the time complexity looks 50 cube, but since we are allowed 50 raised to the power 4, which is well within the time limits, what we'll do is we will do another iteration to make the transitions. So we will iterate on the number of times we get the I plus 1th price. Okay, so this will contribute another nested loop of size 50, and then the time complexity becomes 50 raised to the power 4, which is still fine. So what we are going to do is we are going to iterate on the number of times we pick the I plus 1th price. Let's say it is J1. So let's say we pick the I plus 1th price exactly J1 times. Okay. So now, can anybody tell me how things are going to work? There are two cases. Let me just write down the cases and then we'll see. So first case is that J1 is equal to 0. And second case is that J1 is positive. So can anybody tell me the transition when J1 is equal to 0? That is, we don't pick the I plus 1th price at all. Got it again. Okay, so something unexpected happened. I'm really sorry for that. Okay, so is my screen visible?
yes.
Okay, okay. Yeah, so we were in this case where J1 is equal to 0. So can anybody tell me what happens when J1 is equal to 0? What exactly are going to be the transitions? So this is a really simple case. So what's going to happen is that if we don't pick any price of the I plus 1th type, well, the state which will be is dp of I plus 1, and the number of draws is going to remain j because we didn't pick any price of type I plus 1, and the number of distinct prices is also going to remain k because we didn't pick any price of type j of type I plus 1. So dp of I plus 1 jk plus equals to dp of ijk. So this is a simple transition. So the probability of this state is going to be increased by the probability of this state. I hope this is clear because nothing special is going on. We just don't pick any price of type I plus 1. So basically we are ignoring the type I plus 1 price. So we just increment I by I plus 1. Okay, so this is the easier case where we don't pick any price of type I plus 1. But now comes a more involved case where we pick a price of type I plus 1. Okay, and we are picking exactly j1 prices of type I plus 1. Okay, so can anybody tell me what state will I reach? Don't like, there is no need to tell me the transition, but which state am I going to reach if I pick exactly j1 prices of type I plus 1? This is not very hard. Like, you can tell me what the state is. It's not very difficult to notice. Okay, so obviously I will be turned to I plus 1, dp I plus 1, j minus j1, and k minus 1. So why are you putting minus signs here? Like, why should it be minus j minus j1, and why should it be k minus 1? It should be j plus j1 and k plus 1, right? Because notice that j represents the number of draws, and I already had j draws, and I'm picking j1 awards of type I plus 1, so the number of draws becomes j plus j1. Okay, so the new state is dp I plus 1, j plus j1, and k plus 1. Why? Because the number of draws simply increased by j1, and the number of distinct prices increased by 1 because I am adding the price of type I plus 1. Okay, so this is the new state of my dp. But what about the transitions now? What should it be equal to or plus equal to? Now that's the tricky part here. So any guesses as to what this transition should be? Okay, so let's see what this transition should be. First of all, what is the probability of getting price I plus 1 j1 times? So this is an easy problem. What is the probability of getting the price I plus 1 j1 times in terms of p of I plus 1? We already have these p values computed. So what is the probability that we get the price I plus 1 exactly j1 times? So this is easy. Can anybody tell me what it is? Yeah, great. So this is nothing but p of I plus 1 raised to the power j1. Okay. So will it be correct if I write something like this here, dp ijk? So I already have this probability with me, and I multiply it with p of I plus 1 raised to the power j1. So this makes sense, right? This is sensible. Like, I already have the probability that I'm getting out of j draws, I'm getting k distinct prizes. So I get the I plus 1th prize j1 times, and the probability of that is p of I plus 1 raised to the power j1. And I simply multiply these two values. So it makes sense, right? but actually it is not correct. So there is just one thing missing here. I think there will be other ways we can get to this state. No, that is correct. That is why we are just doing a plus equal to sign. That is why we are not having an equal to sign here, because when we can get to this particular state from other state, then again we are simply adding this value, right? So we will go to all the states from which we can get to this particular state, and then this plus equal to sign makes sure that we take into account all those states. Okay, so that's good enough. But there is one problem with this transition. There is one thing which is missing here. So we have just considered the probability that we get this I plus 1th price J1 times. But we haven't considered the case which J1 times should I get this I plus 1th price. Yeah, so in total, I will have J plus J1 draws. And out of those J plus J1 draws, I should get the I plus 1th price exactly J1 times. And I haven't taken into account exactly which draws should it be. So basically, I haven't taken into account the combinations, the various different arrangements that the prizes can have, such that I get the I plus 1th prize exactly J1 times. I admit that I have taken into consideration all the possible combinations of the prizes of the first I kind, but I haven't taken into consideration all the combinations of the prizes of type I plus 1. So that is one thing which is missing. So I need to multiply it with number of ways to choose J1 draws out of J plus J1 draws, in which, so I will choose J1 draws in which I get price I plus 1 out of the J plus J1 draws. Okay. I have taken into consideration all the combinations of the prices of the first I kind in DP of IJK, but I haven't taken into consideration all the combinations of the prices of type I plus 1, right? So out of the J plus J1 draws, I have to randomly pick J1 positions in which I will get the price of type I plus 1. And so can anybody tell me what will be the number of ways to do that? Out of the total J plus J1 draws, I will pick exactly J1 draws, which will have an award of type I plus 1. So what is the number of ways to pick J1 draws from J plus J1 draws? Right. So it is nothing but J plus J1, C J1. So let's get rid of this and simply replace it with this expression. J plus J1, C J1. Another way to look at it is that we can consider all prices of type less than I plus 1 to be of a particular type, and all prices of type I plus 1 to be of another type. And the number of ways to permute them is nothing but the total number of elements factorial divided by the factorial of the first element into the factorial of the second element, which will be J plus J1 factorial divided by J factorial into J1 factorial, which is nothing but J plus J1 C J1. Okay. So yeah, this is a bit tricky to understand, I admit. So if anybody has any doubts in understanding how exactly this expression is coming into action, then you can ask. Or if it is clear, then it will help me if you just write it is clear in the chat box. Okay, great. If it is clear, then it's really great, because it took me some time to wrap my head around this thing. All right, if it is clear, then this basically completes all the transitions. Great, great. So yeah, this completes the solution. So we have these three states, and we will have another nested loop for these transitions, and then we'll just carry out the transitions, and then we'll look at the final answer. So can anybody tell me what the final answer is going to be? So this is again a very easy problem. So what will be the final answer once I have calculated all the DP values? According to the problem, they have asked us the probability of getting exactly m different prices from the first k draws. So what should be the final answer? right? So it should be, once we have looked at all the prices, we will look at total M draws and we will get exactly K distinct prices. So this is going to be our answer, DPNMK. Okay, great. Great. Everyone is correct. So the final answer is going to be DPNMK once we have all the DP values computed. I still can't properly understand the need for having I as the state. Well, I is in the state because we are looking at the ith price right now, and from the ith price, then we will look at the I plus 1th price, and we will see how many prices of the type I that we are going to pick. So this is somewhat similar to when we do a simple DP on an array. We always keep the index as a state of our DP, right? It's not possible to not keep the index as a state of our DP. Let's say we are calculating the LIS of an array. Then we always keep DP of I, right? Where I is the index in the array. Similarly, here I is the index of the particular price which we are looking at. So obviously that has to be in the state of RDP. Like if I is not in the state, how exactly do you plan to carry out your transitions? This I was crucial because we used I. Yeah, so every ith price is different because the probability of every price is different, right? These P values are different for every price. This is Wi upon sum of all the Wjs. So these P values are different for all the prices. And yeah, that's the main reason why we have to put the price in the state of RDP. I don't really think that we can, yeah, we can maybe optimize on the space if we can definitely optimize on the space. But again, that is going to be like implementation heavy. So we can reduce one state from our DP and we can just keep two arrays. But like that is really not necessary here. So we can definitely optimize on the space complexity here, but that is not really necessary. We can get rid of this I and just keep a two-dimensional variable. Yeah. That's okay, but I don't think that is really necessary. That will just make it implementation heavy. So we are going to skip that because in the liberty that we have in AdCoder problems is that the memory limit is really high as opposed to code forces rounds, right? So yeah, this is the entire solution to this problem. If everything is clear, I will go ahead and code it up. So yeah, let's go ahead and try to code this solution up. So my mod is already set. Again, I will just copy this NCR template code that I have. Can you explain some arguments patterns when prefix can be taken into state space? Yeah, so one thing is that in problems like this, when you are basically out of ideas and you think that there is only the bit mask way to do it, and that bit mask is not going to fit in time complexity, it's a good idea to try to think about taking the prefixes, right? But in general, I don't think there is a very standard notion as to exactly when you should think about this, right? Okay. So we have a few variables. M, K, and capital K. So let's just take the input first. We have N, M, K, and all the weights. So we take in all the weights first, and then we will compute the probabilities, which is easy because we are already computing the sum of all the weights. So we can in O(n) time compute all the probabilities. So probability of I modulo this number is going to be W of I divided by sum, and division under modulo is the same as multiplication of the modular inverse. So it's going to be Wi into the modular inverse of sum, right? Also, one thing which we can do is we can pre-compute this modular inverse. I have this inverse function which basically computes the modular inverse of any number. It uses the extended Euclid's theorem. But what you can do to calculate inverse is that you can just write down this binary exponentiation function, and inverse of a number x is nothing but x raised to the power mod minus 2. That is something that you can do. But I have this inbuilt inverse function. Sorry, not inbuilt, but pre-written inverse function. So we will multiply it by inverse, which is equivalent to division under the modulo sign. So this computes the probabilities. Okay, great. So now what we'll do is we'll create a 3D DP array. So this will be vector of vector of vector. So vector of VLL maybe DP. So first state is the price. So that should be of size n. Okay. And let's look at the second state. So the second state is the number of draws, which should be of size k, right? And the third state is our number of unique prizes that we can get, which should again be of size n, right? So this creates a 3D DP array initialized with all zeros because this element here is 0, right? So now let's write down our base case. So our base case is DP 0, 0, 0, which is equal to 1. And now we will iterate on all the states and just carry out the transitions. So we go from 0 to n minus 1, and then we will iterate for j from 0 to k. And then we will iterate for small k from 0 to m. Okay. And now let's try to iterate on j1. So first thing that we'll do is we'll take care of the case when j1 is equal to 0. So that is nothing but dp of I plus 1 and j and k plus equal to. So since I have to do it modulo something, I won't be able to write plus equal to here. So dp of I plus 1 j k plus dp of I j k mod, right? So this takes care of the case when j1 is equal to 0. And now I will iterate on j1. Okay. So for j1 is equal to 1, and notice that once I take j1 elements of type I plus 1, the total number of draws will be j plus j1, and there is no point in going beyond capital K draws, right? So I will make sure that j plus j1 is less than equal to capital K and j1 plus plus. Okay. So now I will have to multiply something. So let's take a variable mul, which is equal to C of j plus j1 and j1. So if we remember, this is the thing which we had to multiply. So now we will multiply this mul variable with p of I plus 1 raised to the power j1. Okay. So what we do is mul is equal to mul into, so I have this pre-written function of binary exponentiation, which raises any number to any power. So it will be p of I plus 1 raised to the power j1 modulo mod. Okay, so now let's take another variable, call it add. So this add variable will store everything. So this add variable will store this thing. Okay. So this add variable is going to be dpijk multiplied by mul. Mod. And finally, what I have to do is dpi plus 1, j plus j1, and k plus 1 is equal to itself plus add mod. So this basically completes all the transitions, hopefully. I'm sure I would have missed something and it's not going to work in the first try, but we'll try to debug it. And the final answer is going to be dpn, capital K, and M. Okay. If I am not wrong. So the number of tries was capital K, right? Yeah. So yeah, the final. So this should be K and M, not M and K. So hopefully this should work, but I'm not very sure that this is going to work in the first compile. So let's just see. There are no test cases, first of all. Okay, so this is passing the samples, and these samples I think are good enough. So I think this works. Let's just try to submit it. All right, so this works. Great. So yeah, this basically completes both the problems that I had in mind today. So that is it for today. If you guys have any other doubts, then you can ask. Otherwise, I will end this meeting. Yeah. So let me do one thing. I will share this link. Or maybe what you can do is you can just go to this results tab and go to all submissions. And then you can search my ID, which is Sharma Harisam. And I will just share this link. Okay. So any other questions? So if there are no more questions, then I will be ending this session. All right, then. Thank you so much for joining. And I will see you in the next session.